For thousands of years, the monuments of ancient Egypt seemed untouchable. Stones weighing tons, aligned with the stars, carved with a precision that should not have been possible. How did they do it? Today, new evidence uncovers techniques hidden in plain sight, engineering that pushed the limits of the ancient world. This is the real story of how the Egyptians built the impossible.
Welcome to the Deep Dive, the place where we dig into the most detailed research, the archaeological reports, and all the experimental work to give you the full story. Today, we are tackling one of the greatest technical puzzles in all of human history, the engineering marvels of ancient Egypt.
We are indeed. And, for centuries, the sheer scale of what they did, the pyramids, the obelisks, it's led to just endless speculation. When we struggle to even imagine doing it today, the easy answer for a lot of people is to say it was, well, magic or something impossible.
Right. And that's the exact narrative we really want to get past today. The fascination with, ancient mysteries often completely misses the point, which is the incredible, staggering human brilliance that was actually at play.
Precisely. So our mission today is to move beyond all that speculative fluff. We're going to be looking at the hard evidence archaeological finds, expert analysis, and especially experimental archaeology, where people are literally recreating these ancient methods.
So we can finally get to the real blueprints.
Exactly. We're going to try and reveal the ingenuity, the sophisticated material science, and the applied physics the Egyptians were using to build for eternity.
So the big question for this deep dive is this. How on earth did they achieve this near impossible precision, moving and working hundreds of tons of rock centuries before we had modern physics or the tools we just take for granted? It's a journey that's going to take us from the stars right down to the sand on the ground. Okay, so let's start with that foundational idea. When you look at the pyramids of Giza, especially from the air, the first thing that just hits you is the mathematical perfection of it all. That north-south alignment is almost impossibly precise. Why was that so important?
Well, it wasn't just about, good aesthetics or making things look neat. It was an absolute theological requirement. The alignment was the physical proof of their entire belief system about the afterlife.
So how does a religious idea translate into a technical need for true north?
So the Egyptian idea of the afterlife, it was tied to a very specific destination in the sky for the soul of the dead king. The king needed to be transported to the circumpolar stars.
Ah, the circumpolar stars. Okay, so these aren't just any old stars in the sky.
No, not at all. There are the constellations that, from the perspective of Egypt, seem to circle around the celestial pole. But the crucial thing is, they never set. They never, ever dip below the horizon.
They're the constants, the one permanent thing in the sky that's always changing.
Exactly. They are the ultimate symbol of eternal life, this undying, unending presence. So by aligning the pyramids so perfectly north-south, the Egyptians were literally building a physical pathway, a conduit, linking the king's final resting place to that promise of eternal life in the northern sky.
So the precision wasn't just a bonus feature, it was the whole point.
It was everything.
But, okay, to get that kind of spatial alignment, you first need temporal precision. You have to be able to tell time at night with incredible accuracy. And that suggests they knew a lot more about astronomy than people usually give them credit for.
And that brings us right to the work of Egyptologist Christian Lykes, who's an expert in these ancient star-based clocks. We have hard physical evidence that shows they were tracking the heavens to measure out the night.
And the clearest example of this is on a 4,000-year-old sarcophagus lid, of all places. On the underside of it, they found what's called a diagonal star clock, a diagonal sterner.
Yes, and this is one of the earliest, most amazing examples of applied astronomical timekeeping we have. It was a really sophisticated grid that tracked the rising and setting of specific groups of stars they called the decans.
The decans. Those are the star groups that rise one after the other over a 10-day period, right?
That's right. And the clock was basically a grid, a star map that cross-referenced the calendar. It let them translate the movement of the sky into reliable segments of time.
So by tracking these stars rising and setting in sequence, they could divide the entire night into 12 distinct hours. But here's the question. The length of a night changes through the year. How did the clock deal with that?
Well, that's the genius of it. Unlike our modern clocks with their fixed hours, the diagonal star clock created unequal hours. An hour would stretch or shrink depending on the season.
So there were always 12 hours between sunset and sunrise, no matter if it was the middle of summer or the dead of winter.
Exactly. The diagonal lines on the grid mapped those changes across the year. It was a living clock designed to work with the sky, not against it.
Incredible. And this wasn't just for, academic curiosity. This was critical for state rituals, which brings us to the role of the Stundenpriester, the hour priest.
A very important job. The hour priest was likely a high-ranking official whose entire responsibility was this meticulous observation of the stars. They'd probably be up on a flat temple roof with a clear view of the horizon, watching for the deacons to rise and set.
So they were the official timekeepers, making sure every nightly ritual happened at the exact right moment.
Absolutely. Think about it. If the king's eternity depends on celestial timing, then the rituals supporting that have to be perfectly punctual. And that precision feeds directly into the engineering. To check the alignment of a pyramid, you have to do it at night, using the stars.
So if the hour priest can define the exact start and end of an hour, the surveyors can schedule their alignment checks with military precision.
Precisely. The ritual need created the technological precision.
What's so amazing is that we're still discovering more about this. The knowledge isn't lost, it's just hiding. Which takes us to the Esna Temple.
The Four Hall at Esna is just. It's an astroarchaeologist's lottery win. It dates to the Greek-Roman period, around the 1st century AD, but it took years of painstaking work to see what was there.
And why was it hidden for so long?
Centuries of soot and grime from open fires had just coated everything. The reliefs, the ceiling, it was all black. But that layer of dirt, ironically, also preserved what was underneath.
So the current project there is basically a massive, very delicate cleaning job.
That's a good way to put it. And as they remove the soot, the original vibrant colors and unbelievably detailed astronomical scenes are coming back to light. For example, they're finding these incredible detailed images showing the different phases of the moon.
How did they symbolize the moon phases?
They use the famous symbol of the Eye of Horus. This directly links one of their most powerful religious symbols to a very real, quantifiable astronomical cycle. It just shows how seamlessly they blended myth and science.
But the discoveries didn't stop there, did they? They found something that was never even finished.
They did, these hidden gems, as they call them. Some of the scenes and inscriptions were only ever sketched onto the stone. They were never actually carved.
And because they were just drawings, they were completely invisible under all that soot.
Completely. So now we're seeing them for the first time. Previously unidentified constellations, new astronomical diagrams. It's like finding a lost chapter of their scientific knowledge.
So let's bring all this celestial knowledge back down to the ground. If they could track the sky with this level of detail, then aligning the pyramids perfectly becomes, well, not easy, but a solvable problem.
It becomes a solvable problem, yes. It's an incredibly elegant solution that's all about observation and geometry.
So walk us through it. How does an ancient surveyor use a star to find true north?
Okay, so the technique is actually quite simple in principle. You pick a bright star in the northern part of the sky. Then you mark the exact point on the horizon where it first rises. After that, you just wait for hours until that same star is about to set. And you mark the point where it's at the exact same altitude as it was when it rose.
So you're finding two perfectly symmetrical points on its arc across the sky.
Precisely. And the line connecting those 2 points, the rising point and the setting point, gives you a perfect east-west axis.
And then the line drawn at a right angle to that is true north. That is stunning. But I have to ask, how accurate could they really be? I mean, on a windy night in the desert with just basic instruments, the margin for error seems huge.
You'd think so. But the accuracy they achieved is what really blows the mind. The Great Pyramid at Giza is aligned to true north with an error of less than 3 arc minutes. That's less than 1/20th of a single degree.
1/20th of a degree over a base that's 230 meters long. That's better than many modern buildings built with lasers and GPS.
It is. It just proves their field methods were practically flawless. They must have used very sophisticated sighting tools, maybe a fixed pillar and a double plumb line, to make sure those marks were perfect. It highlights that this precision wasn't a lucky guess. It was systematic, disciplined, applied geometry.
So now that we know they could find true north, we have to tackle the next problem. How do you translate that perfect measurement into tons of granite? We have to go from the cosmos down to the quarry floor.
And this is where a lot of people get stuck. It's one thing to align a structure. It's another thing entirely to drill perfect holes and get a mirror polish on some of the hardest stone on the planet, like granite and diorite.
The evidence is just undeniable, though. Archaeologists find it all the time. The source mentions a perfect door hinge from the Temple of Heliopolis, a perfect circle drilled through hard stone.
Right, and that physical proof is what drove experimental archaeologists like Ole Hoffman and Harm Paulson to actually try and replicate the techniques themselves. They wanted to figure out what tools the stone borers were actually using.
So let's talk about the tools. What did they find?
Well, from the marks left in the stone, they could tell it wasn't a solid drill bit like we'd use today. It was a hollow tool. It was a copper tube.
A copper tube. But copper is soft. Granite is a 6 or 7 on the Mohs hardness scale. Copper wouldn't stand a chance. It would just get flattened.
Exactly, and that's the key. The copper wasn't doing the cutting. It was just the delivery system. The real secret was the abrasive they added to the process.
Ah, the material science breakthrough. And the sources point pretty strongly to the Greek island of Naxos, which supplied something called Naxos emery.
Naxos emery, yes. It's a type of rock that's mostly corundum. And here's why it's the game changer. Corundum has a hardness of 9 on the Mohs scale.
Okay, let's put that in perspective. Diamond is a 10. So Naxos emery is almost as hard as diamond. And it's much, much harder than the granite it's supposed to cut.
Way harder. So the technique was to use what's called a fiddle drill. It's like a bow that spins the copper tube back and forth really fast. As it spins, they'd pour in a slurry of this Naxos emery grit and water.
So the soft copper tube is just pressing those super hard grains of emery against the granite and grinding it away.
It's pure abrasion. Those tiny, sharp grains are doing all the work. It's essentially the exact same principle as a modern diamond drill. They were using the hardest natural material they could get their hands on, combined with mechanical leverage, to get these perfect results.
That is just a phenomenal insight. It takes the whole process from mystery to applied science. But it must have been unbelievably slow.
Oh, it was painfully slow by our standards, but it was still faster and way more precise than just pounding away at it, and the hollow tube was efficient. Once you drilled deep enough, the core of stone left inside the tube could just be snapped off and removed.
Right, leaving a perfect hole.
Yeah.
You find those cores in the quarries.
You do, and they had a backup plan, too. If they couldn't get the imported emery, they used something more common, dry quartz sand.
Which is still pretty hard. About a 7 on the Mohs scale.
Hard enough to work, it would just take longer. The key was their understanding of the power of that abrasive grit when applied with constant pressure and motion.
And this wasn't just for drilling holes, was it? This same principle was used for finishing the surfaces of things like obelisks.
Absolutely. To get that almost mirror-like polish on a granite obelisk, you need to use the same principle. Teams of workers would have spent months, maybe even years, rubbing the surface with grinding stones and an emery slurry to smooth it down. It was a comprehensive method for all stoneworking.
Okay, so they knew where north was, and they knew how to cut the hardest rock on Earth. Now for the really big one. Moving it. We're going from the fine grit of the abrasive to the sheer mass of hundreds of tons of stone.
And this is where we have to talk about the obelisks. These are just true wonders. Not built from blocks, but carved from a single piece of stone. A monolith, weighing hundreds of tons.
And they were symbolic, right? Representing the sun god Re and the king, so they had to be perfect. No cracks. The big mystery has always been how they were quarried, moved, and raised without just snapping under their own weight.
It's a puzzle that consumed the researcher Armin Wusching. And his whole philosophy, which is so important here, was to think Egyptian, to forget modern tools and try to figure out the logic they would have used.
And we know all the big obelisks came from the quarries near Aswan, and that's where we find one of the biggest clues of all, the unfinished obelisk.
The unfinished obelisk is it's a gift to archaeology. It was abandoned right there in the quarry because a crack appeared in the stone as they were working on it. Because it never moved, it's like a giant open-air instruction manual.
You can see every stage of the process.
You can. You can see the marks from the dolerite pounders they used to chip away the surrounding rock. You can see how they planned to detach it. It's all laid out for us.
And the speed at which they worked is just mind-boggling. The sources suggest they might have managed to quarry and transport 2 obelisks to Karnak in just 7 months.
Which is an incredible feat of logistics. That's not just a few artisans. It's a massive industrial-scale operation running with military precision.
So once the obelisk is freed, the first problem is moving it from the quarry to the Nile. The early theories were all about dragging it overland.
Right. The first idea was loading it on a massive sled and pulling it over wooden rollers. Then some tomb paintings suggested they might have dragged the sled over wet sand.
And that wet sand trick is real, right? It cuts the friction by about half.
It does. But here's the problem. When your object weighs hundreds of tons, cutting the friction in half still leaves you with a massive amount of force needed. You're talking about hundreds, maybe thousands of men pulling on ropes.
And that creates a logistical nightmare.
A total nightmare. Imagine the congestion. Trying to coordinate thousands of people in a narrow space, it would be chaos. It's just not efficient.
So the conclusion is that the overland journey must have been much, much shorter than people thought.
Exactly. And that led a team of geologists to look for an alternative. And they found pretty good evidence for what they call the canal theory.
Tell us about that.
They found geological signs that a spur canal was dug during that era, running directly from the quarry area to the Nile harbor.
Which, if it existed, completely changes the math. It means the overland drag might have been just a few hundred meters, not kilometers.
A much more manageable distance. It turns the main journey into a water-based transport problem, not a land-based one.
But even for that short distance, you still have to move a 300-ton stone. And this is where Armin Wersching's ideas about energy efficiency come back in.
Right. Wersching didn't think simple pulling was clever enough. He proposed something called the lever hub principle.
The lever hub principle, how does that work?
The idea is you place strong hardwood beams under the obelisk at regular intervals. Then, instead of pulling, teams of men would use levers in a synchronized rowing-like motion to push down on the beams.
So you're not fighting friction horizontally. You're applying force vertically with a massive mechanical advantage. It's like rowing the stone across the ground.
It's a great analogy. It's a much more efficient use of manpower. It allows for slow, controlled, powerful movement to get the monolith to the edge of the water, ready for the next, even bigger challenge.
Getting it on a boat.
Now the problem gets even bigger. You've solved friction on land, but now you have to deal with buoyancy and stability on the water. How do you load that much weight onto a wooden ship without it just capsizing on the spot?
It all comes down to Archimedes' principle, right? Water displacement. A huge steel ship floats because it displaces a massive amount of water.
Yes. And this is where Wersching's most radical idea comes in. He believed the Egyptians understood and applied this principle a full millennium before Archimedes ever wrote it down.
So you're saying they had a working practical knowledge of hydrostatics. What's the evidence for that, other than the fact they succeeded?
Well, the success is the main evidence, but the physics are undeniable. An obelisk that weighs 300 tons in the air loses almost half its weight when it's submerged in water. If you can use that fact to your advantage, the loading problem becomes, well, not easy, but solvable.
Right. If the effective weight is cut in half, the ship you need doesn't have to be quite as ridiculously huge.
Exactly. And Wersching proposed a very clever method to do it, using a double ship design.
Okay, so walk us through this step by step. How does this water loading process work?
First, they build a special piece of infrastructure in the harbor. The obelisk is maneuvered onto an underwater pedestal. So right from the start, most of its weight is already supported by the water.
So it's already lighter before they even try to lift it.
Then you bring in the double ship. That's two hulls, rigidly connected by a huge deck. This ship is filled with ballast rocks, sand, whatever, to make it ride very low in the water. They then sail it directly over the submerged obelisk, straddling it.
So the low-riding ship is positioned over the obelisk. Then what?
Then they secure the obelisk to the ship with massive ropes and timbers. And here's the genius part. They rapidly remove all the ballast from the two hulls.
And as the ballast goes out, the ships become much lighter, and their natural buoyancy just pops them up.
It pops them up, lifting the obelisk right off the pedestal, suspended securely between the two hulls. They're using buoyancy as a crane.
That is just... it's breathtakingly clever.
It is. And of course, you need an incredibly strong timber structure connecting those two hulls to keep it stable for the whole journey down the Nile.
Okay, the double ship makes sense for the river. But many of these obelisks ended up in Rome. That's a 2,000-kilometer journey across the open Mediterranean Sea.
And that is a whole different level of challenge. You're going from a calm river to unpredictable open seas. A 300-ton rigid piece of cargo is not something you want shifting around out there.
Wersching believed they used a modified double ship even for that sea journey.
He did. But that's where we have to bring in some healthy skepticism from other experts like Christoph Schaefer, who is an authority on ancient seafaring.
And Schaefer has his doubts about the double ship on the open sea.
He does. He points out a major structural flaw. The problem is trying to get two separate hulls to move in perfect sync through complex waves.
What's the specific problem?
Well, a single hull moves as one unit. It flexes and rolls with the waves. But if you rigidly connect two hulls, one might be on the crest of a wave while the other is in a trough. that creates enormous twisting forces, torsion on the structure connecting them.
And that twisting force could just tear the whole thing apart mid-journey.
That's the risk. It's an immense engineering challenge. Wershing actually proposed a counter-solution, which was even more complex, adding a third ship.
A third ship.
Yes, a third hull at the front, acting as a common bow to stabilize the other two. It's an incredibly complicated arrangement, but it shows they were thinking about these stability problems.
But what Schaefer's critique really confirms is that the Romans were incredible seafarers. They knew what was possible. So whatever solution they used, it must have been sophisticated enough for the job.
Absolutely. The capability was there.
So let's say the obelisk makes it across the sea. It arrives. Now comes the final spectacular act, raising a 300-plus-ton stone monument from horizontal to vertical.
This is the grand finale. This is where you have to overcome pure gravity.
And to really appreciate what the Egyptians did, we have a great point of comparison from thousands of years later in the 16th century.
We do. We have detailed reports about the re-erection of a 300-ton obelisk in Rome during the Renaissance. It was a massive public spectacle.
So what did it take for Renaissance engineers, with all their advanced knowledge, to do this?
The resources they needed were just staggering. It took 900 men, 150 horses to power the machinery, hundreds of meters of rope, and a massive, complex system of 47 different winches, all working in unison.
47 winches, 900 people, all pulling and cranking in perfect sync. That was a major technical achievement for its time.
A huge achievement. And this is the crucial point. The ancient Egyptians did the same thing, or even greater feats, thousands of years earlier. And they did it without iron, without horse-powered machinery, and without Renaissance physics.
They did it with wood, rope, and brilliantly organized human power.
Which brings us back to Wershing's ideas about leverage. It wasn't just about brute force. It was about the clever, systematic application of mechanical advantage to multiply the force of every single worker.
It seems like their greatest skill wasn't just engineering stone, but engineering people, orchestrating thousands of individuals in a single high-stakes, flawless operation.
It really is. The monuments we see today aren't just a testament to their building skills, but to their incredible project management.
So if we pull all of this together, the big takeaway from this deep dive is that the solutions weren't magic. They were just hidden under soot in a temple, or misunderstood in the marks left in a quarry.
Exactly. We've gone from speculation to process. What we see is the result of advanced astronomical calculation, a deep understanding of material science like using emery, and incredibly innovative mechanical engineering.
It's the lever hubs. It's the understanding of buoyancy. It was all practical, applied science.
They solved these huge logistical challenges because they thought creatively. They used the principles of physics and geometry with the materials they had to achieve things that still seem impossible.
And that journey from using stars to find north, to using wet sand to beat friction, to using water's buoyancy to lift stone, it just reinforces this idea that real innovation happens when you're forced to think differently. They really did think Egyptian.
And that brings us to a final thought for you to take away. The source material mentioned a quote from the author Astrid Lindgren, who said, "Everything great that happened in the world first happened in the imagination of people."
So if these incredible technical achievements, things that still boggle our minds today, began as just an idea in the imagination of an Egyptian engineer or priest, what seemingly impossible challenges are we facing today that are just waiting for a new perspective, for a fresh look at the underlying physics?
The Egyptians proved that constraints are the mother of innovation. Keep questioning the impossible.
That's it for this deep dive. We will catch you next time.